In continuation of the topic on machines, today we shall discuss levers. So this is the very simplest form of machines, or you can say that in our daily life, probably the simplest form of a machine is a lever. So a lever is basically a straight rod or a bent rod or a bar that is capable of rotation about a fixed axis. So you can say that a lever is a rigid rod or bar that is either straight or it is bent. But it is capable of rotation about a fixed axis. Capable of turning or rotating about an axis. Now the axis is an imaginary line that passes through a point which is called as the fulcrum. The axis passes through the fulcrum. Through a fixed point. Fixed point which is called as the fulcrum. Fulcrum, or you can call it as pivot also, which is also popularly called as pivot. Sometimes there are hinges present at the position of the fulcrum also. So a lever is just a rigid rod, but whenever we say rigid, it is not absolutely rigid because none of the materials available is 100% rigid, but still from the point of view of application of the lever, we can assume that the rod is nearly perfectly rigid rod, which is capable of rotation about an axis. So now levers are generally of three types. Three types of levers are available as per our use in daily life. So these levers have been classified as levers belonging to class 1, levers belonging to class 2, or levers belonging to class 3. Class 1, class 2 levers and class 3 levers. Now the classification is on the basis of the position of the fulcrum and the effort applied and the load that the lever is capable of lifting. So with respect to the fulcrum, the effort applied and the load that the lever can lift, class 1 lever refers to the situation where the fulcrum is always between the load and the effort. So a simple class 1 lever will be of this type. Suppose the fulcrum is somewhere between. It is not necessarily that the fulcrum denoted by F is at the middle position. It is somewhere in between the load and the effort. So suppose at one end the effort has been applied and at the other end there is the load which the lever is capable of lifting. So if the fulcrum lies between the effort and the load, it is called as class 1 lever. Class 2 levers are those in which the load lies between the fulcrum and the effort. So suppose effort is at one end of the rigid rod, the load lies between the fulcrum and the effort. So suppose the fulcrum is at one end and the effort is applied at the other end, and the lever is capable of lifting a load somewhere placed in between. So class 1 fulcrum is between effort and load, class 2 load is in between fulcrum and effort, and the third obviously will be class 3, where the effort will be in between the fulcrum and the load. So class 3, schematically you can represent it as fulcrum at one end, the load at another end, and effort somewhere in between. So these are the 3 classes of levers that are used in our daily life. So when we try to analyze the performance of a lever, we again have to find the mechanical advantage and the velocity ratio. So by the definition of mechanical advantage, it is the ratio of load to effort, and by the definition of velocity ratio as distance moved by effort to distance moved by load, we can thereby calculate the efficiency also. So let us move on to the principle of levers, that is general to all the class of levers that is available to us. So let us go on to the principle of levers. The principle of levers is specifically the principle of moments that we have already studied. So levers work purely on the basis of the principle of moments. The principle of moments refers to the situation where the sum of clockwise moment and the sum of anti-clockwise moment is same. So we can say that the principle of moments when applied to levers will be the clockwise moment of the load about the position of the fixed point, that is about the fulcrum. Clockwise moment of the load about the fulcrum is equal to anti-clockwise moment of the effort about the fulcrum. Now this statement can be interchanged with respect to the position of the load and the effort. We can also call it as anti-clockwise moment of the effort about the fulcrum is equal to the clockwise moment of the load about the fulcrum. So it depends on how the effort and the load has been positioned with respect to the fulcrum. So if you look around the definition of class 1, class 2 and class 3 levers, you can see that the position of effort and load is interchangeable, at least for the class 1 lever. Now for the class 2 and the class 3 lever, the fulcrum could have been at the rightmost end and the effort could have been in the position of the fulcrum. So what matters is the position of the fulcrum with respect to effort and load. In case of class 1, it should be in between. With respect to class 2, load should be in between the fulcrum and the effort. That means the position of the effort and the fulcrum are interchangeable. And for class 3, it is the effort which should lie between fulcrum and load. So position of fulcrum and load is then interchangeable. So this definition could have changed accordingly, but the principle remains the same. Clockwise moment of load could have been replaced by clockwise moment of effort, and anti-clockwise moment of effort could have been replaced by anti-clockwise moment of load. But the message of the principle is straight and simple. It is based upon the principle of moments. So let me consider any one lever and try to analyze the mechanical advantage of that particular lever. So let me consider the case of class 1 lever, suppose. So this is the position of the fulcrum, suppose this is the position of the load, and this is the position of the effort. Let me call one end of the lever as point A and another end as point B, and let the fulcrum be F. So the distance between the effort and the fulcrum, this is called as the effort arm. So the effort arm is simply the distance between the effort and the fulcrum, which we can call as FB as per this diagram. The distance between the load and the fulcrum is the load arm, and as per this diagram, this is AF. So by the principle of moments, as you can see in this diagram, the effort will create an anti-clockwise moment, clockwise moment about the fulcrum, and the load will create an anti-clockwise moment. So therefore, by the principle of moment, both the moments are exactly equal and opposite. So you can write load into load arm. Load into load arm, that is AF, that must be equal to effort into effort arm, that is FB. So you see that load by effort becomes FB by AF. Now what is load by effort? It is the mechanical advantage of the lever. Mechanical advantage, the definition is load by effort. So this is FB. Now what is FB? FB is effort arm. So I can say that mechanical advantage is equal to effort arm divided by AF, that is the load arm. So in the case of levers, we can have mechanical advantage as effort arm by load arm. So if we take class 2 levers also, the load lies between the fulcrum and the effort. So this is the load, this is the effort, and this is the position of the fulcrum, suppose. This is the position of the fulcrum. So in this case also you can see that the load is creating a moment, the effort is creating another moment. The load is creating a clockwise moment in this class 2 lever. The effort is creating an anti-clockwise moment. So again, by the principle of moments, you can say that this load into load arm, suppose let me call this point as A and this point as B. So the definition remains the same. L into AF must be equal to E into BF or FB. Similarly, for the class 3 levers, effort lies between the fulcrum and the load. So let me call this end as B. The effort end is called as B end. And the effort is applied, and the load end suppose we called as A. So again this statement remains valid here. You see that this effort is creating an anti-clockwise moment and this load is creating a clockwise moment. So load into load arm, that is L into AF. L into AF is effort into effort arm, that is E into FB. So this statement remains valid as per all the classes of levers that we have discussed. So now we can say that for lever, the mechanical advantage is definitely effort arm and load arm. Now, as you can see that if effort arm is greater than load arm, the mechanical advantage will be greater than 1. So the lever will act as force multiplier. If the load arm is greater than the effort arm, then the mechanical advantage will be less than 1. It will act as a lever to obtain gaining speed. And if it is both are equal, effort arm and load arm, then mechanical advantage will be equal to 1. And the simple application is that we are trying to apply the effort in a convenient direction. So this situation is available for all the kinds of levers. Now, if you look at class 1 lever, you can see that the fulcrum might be towards the load end, close to the load end, or the fulcrum might be close to the effort end, or the fulcrum might be exactly in between the load and the effort. So, for the class 1 lever, we have all 3 possibilities. Mechanical advantage might be greater than 1, might be less than 1, might be equal to 1. However, in the case of class 2 levers, as per the position of the load, effort and fulcrum, it is obvious that in the case of class 2 levers, the effort arm is definitely larger than the load arm. the effort arm, that is FB, which is definitely greater than AF, that is the load arm. So the effort arm greater than load arm means that class 2 levers are always used as force multipliers. That means by applying a lesser effort we can lift a large load. And for the class 3 levers, it is quite obvious as per the position of the load, the effort and the fulcrum. The effort arm is less than the load arm. You see that the effort arm here, in this case, that is FB, which is definitely less than AF. So effort arm is less than load arm. So in the case of class 3 levers, they are always having mechanical advantage less than 1. So they are used to obtain gain in speed. But all the facilities are available in the case of class 1 levers. They are either of mechanical advantage greater than 1, less than 1, or equal to 1. So there are several examples of this. So for class 1 levers, you can have a variety of examples. You can refer to any standard textbook, but still let me give a brief overview. Class 1, where mechanical advantage is greater than 1. So in the cases of certain devices, like you can say crowbar or claw hammer or pliers or shears, in those cases the mechanical advantage is greater than 1. That means they are used as force multipliers. And such devices are shears. The shears are used to cut metal sheets, and for shears definitely they have long handles as compared to the blades. So the effort arm is greater than the load arm. Not only that, claw hammer, plier, crowbar, all are having mechanical advantage greater than 1. For mechanical advantage equal to 1, there is the best example is the physical balance. The physical balance is a device which is definitely a class 1 lever and its mechanical advantage is equal to 1. So in these cases definitely both MA and VR are greater than 1, and MA and VR are both equal to 1 for physical balance, and MA less than 1, that means they are used to obtain gain in speed. Sometimes it is also called a speed multiplier. VR is also less than 1. So example is scissors, which are used to cut paper or cloth. And simple such applications are also available in different types of class 1 levers. We can compare scissors versus shears also. In the case of shears, which are used to cut metal sheets, the handles are long, whereas in the case of scissors, which are used to cut cloth or paper, the blades are long. So both are class 1 lever, but one is having mechanical advantage greater than 1 and another is mechanical advantage less than 1. So let us move on towards the class 2 levers. Now class 2 levers, as I have already discussed, their mechanical advantage is always greater than 1. There is only one application of these. For all class 2 levers, both mechanical advantage is greater than 1, velocity ratio is greater than 1. They are purely used as force multipliers only. So by applying lesser effort, we can lift large loads. The best examples that we use in our daily life is a bottle opener, a nut cracker, and many more. Paper cutter, everything, they go under the class 2 levers. And if we move on to the class 3 levers, we will also get variety of examples, but they are purely used to obtain gain in speed. So if we go on to class 3 levers, so they have always mechanical advantage less than 1 and velocity ratio also less than 1, and definitely they are used to obtain gain in speed. And several examples of class 3 levers are sugar tongs, fire tongs, and many more. Spade, etc. You will get variety of such examples in different textbooks. But you have to remember the basic principle and the utility of the levers on the basis of their mechanical advantage and their velocity ratio. Let us solve two problems related to levers. The first problem is as per this diagram. It has been asked to identify the class of the lever. FA is 60 centimeter, AB is 40 centimeter. We have to find MA and we have to find E. So obviously for the class of lever we have to identify the position of the fulcrum, the effort and the load. As you can see as per this diagram, the load is between the fulcrum and the effort. So definitely this is a class 2 lever. So class 2 levers means the load is in between the fulcrum and the effort. Now FA is 60 and AB, mechanical advantage. We know that mechanical advantage is effort arm by load arm. For levers it is effort arm by load arm. Effort arm means distance between effort to fulcrum. So that is BF or FB divided by load arm, that is obviously A to F. Distance between load and fulcrum. So this is AF. Now FB is definitely AF plus AB. So this is FA plus AB by AF or FA, whatever you say. So you see that FA is 60 and AB is 40. So this is obviously 60 plus 40, that is 100. By what is FA? FA is 60. So this is 100 by 60, that is 10 by 6. That is obviously 5 by 3. So 5 by 3 will be the answer for mechanical advantage. You see that it is a class 2 lever, so mechanical advantage is 5 by 3, which is obviously greater than 1, and they will be acting as force multiplier. Now it is given to find E or the effort. We know that mechanical advantage is also load upon effort. So therefore we can say that load, that is 10 by effort E, is obviously the mechanical advantage value that we have calculated, that is 5 by 3. So from this you get effort as 5 into 2, 6 kgf will be the value of the effort. So you see that we are lifting a load of 10 kgf applying an effort of 6 kgf. So obviously by applying lesser effort we are capable of lifting a larger load, that is the application of class 2 lever. So now for the second question, again we have to identify the class of lever. In this case you see that the effort is in between the load and the fulcrum, so obviously this is class 3 lever. Class 3 levers are which those have effort arm in between the fulcrum and the load. Now again it is given that FA is 20 centimeter and AB is 430 centimeter. We have to find MA. So by the definition of MA, it is effort arm by load arm. So what is the effort arm? Effort arm is distance between effort to fulcrum, that is FA, by load arm, distance between load to fulcrum, so that is FA plus AB. So what is FA? FA is 20 centimeter and AB is 430. So AB 430 plus FA 20. So this is 450. So that is 2 upon 45. So So you see that mechanical advantage is definitely less than 1. So these are levers which are used to obtain gain in speed. Now the last question is we have to find E. We know that mechanical advantage is load by effort. So therefore the value of load is given 55 by effort is equal to the value of mechanical advantage that we have calculated 2 by 45, which means that effort is equal to 55 into 45, and definitely you can calculate 55 into 45 by 2. So this much Newton will be the value of the effort in this case. So you see that effort is quite large as compared to the load, but the principle of class 3 levers is to obtain gain in speed. We are never trying to say that we are trying to lift larger effort using lesser load. The situation or the application is that we are trying to move faster the load by applying the effort. That means we are trying to achieve what is called as gain in speed. So because we are trying to achieve gain in speed, the effort arm is definitely less than the load arm. The load arm will be quite large.